under simulation, we talked about reservoir waiting, and today we will be going into another area, simulation in the oil industry, specifically talking about healthy simulation. Right? It's a very interesting area of simulation, area that you as a oil and gas student or oil and gas person that wants to learn or know anything about simulation must understand or should understand. So we'll take it in the try to put it in an elementary form or in a basic form that will be easy for you to understand and flow. So the first question I'll be talking about is what is height spend height. What is height spend height? What aspect? When we're talking about aspect hysis, referring to a chemical process simulation tool. It is a chemical process simulation tool. The chemical process simulation tool. I hope you can hear me. So Arsenal is a chemical process simulation tool that enables us okay, to solve this
Please let us hold on for our lecturer. Will join us very soon. Please let us wait patiently for our lecturer. Engineer, please unmute yourself.
Okay, I hope you can all hear me. I want to believe you can hear me. If that is so, um, and I want to also believe you can see the screen. Mr. Yomi, please share the screen of the second system, the one that is muted. Please activate the sharing of the screen. Okay.
I've ready. I'm working on it.
Okay. All right. I'll just go on. So as I was saying, um, when we're talking about ISIS, what we are referring to is a simulation tool which enables us to carry out chemical process simulation. Chemical process simulations. What do I mean by chemical process simulation?
Now, every activity that you have to carry out, every activity that you have to carry out with regards to processing any chemical. Let's take crude oil. In this case, we're dealing with oil and gas management. All right. So take crude oil for instance. Take crude oil.
Engineer Emma, you have muted both devices. Please unmute one. Engineer Emma, you have muted both devices. Please unmute one.
I've unmuted one, the one I'm using.
All
I've
right, all right.
unmuted.
We can hear you.
All right.
We can hear you.
Okay. So, as I said, as I was saying rather, crude oil contains several components. So, if we are going to carry out, and it undergoes several um processes until you even have your fuel or your gas or the other fractions that you eventually get at your dispensing stations, all right, or your filling stations. So, what does this mean? We can actually, before we start creating or installing these um processing component, before you start installing your of constructing your process area, your refinery and the rest of them, the first thing you do, like what I said in our very first class when I talked about feed, front end engineering design, the first thing that is expected of you to do is to carry out a modeling. You understand? You design it. The design front. That's why it's called front end engineering design. After you've done the planning, you've taken data from the laboratory about the components of the crude oil and the rest of them. Before you are going to do some different types of modeling. There's the modeling that will involve the 3D modeling, where you use plant design management system tool or auto plant 3D. Those are design tools for build, like constructing, showing how it's going to look like. It's just like I explained much earlier, when you're talking about architectural designs. For instance, you want to build a house, you do some architectural designs, and then that design will now be like a guide to see how or what you want to build, how it's going to look like, and all that. You also do some calculations, the 2D designs that shows how the space is going to be measured, all the measurements spelled out exactly the way it is in civil engineering or in architectural designs. We also have the same thing in oil and gas management. So even before from drilling, from the process of exploration or drilling down to the refinery or the flow station, where it's going to undergo some separations, where we are going to do fluid characterization or gas gathering, or name it, or whatever processes that the crude oil is going to go through. We first of all have to simulate it. We first of all have to do a design, so we eventually get to know what the dynamics is going to be like, what calculations are going to be involved there, what's going to be happening in the flow station that we want to design, or the operations that we are going to be carrying out. Everything that is going to be happening in it is first of all designed, so, or simulated. So one of the simulation tools that we use is our HYSYS simulation. We call it HYSYS chemical, for chemical process simulation. All right. This this tool, this thing I'm introducing to you, or we're introducing to you in JPTS, please take it very serious. Thank God many of you are in your finance here, and after now you'll be going for certification. So this is something that is of great value. Of great value. You need to understand it. All right. So simulation. What do we mean by simulation? We are talking about the use of a computer program to quantitatively model the characteristic of what, or the characteristic equation of a process in terms of material and energy stream. You can see that. Okay. I believe you can see this. You can all see the screen. So everything I've just explained about simulation is explained here. That we make use of we are making use of what now? A computer program to quantitatively model. Quantitatively, why are we talking about that? Because we'll be dealing with volumes, quantity, flow rates, and the rest of them. So we would need to model it quantitatively. And what are we modeling? The characteristic equation of a process. Everything that is going to be happening there is the characteristic equation of the process. You can see something here is like we're putting the periodic table of all elements. You are putting it into something, and you're also having a calculator. That's just like a symbol to show you that we'll be doing some the system, a computer kind of helps you calculate. So a lot of complex equations and calculations that you would have been able to that you would have been cracking your head to do, the system does it. HISIS does it for you. ISIS is one of the leading, in fact, one of the topmost leading, is arguably the topmost leading simulation, chemical process simulation tool that we have in the industry. After you've done the simulation, it also helps you generate all the equations and puts them in a tabular form that it can now be interpreted. So usually when we're when we're even going back to design or construction, most of the data that we use are what we have obtained from HISIS simulation. All right. Now, it's a basic principle. We start from the known feed, the fluid, the mole fraction. Well, you know what mole fraction is. I believe you've done chemistry in your basics. So the mole fractions, the mole ratio of each component in that fluid, being crude in this case. Fluid, I mean FLUID. All right. Now, so we put them into a given process model, which is HISIS, then it predicts the product for us. So whatever process that we are going to be doing, this is just an illustration of what it looks like. You are going to be seeing more. So some of the principles that we'll be following that HISIS operates under is on process design analysis. Process design and analysis. It designs the process for you, it analyzes it. Another benefit, another thing, principle it works on is optimization. So with HISIS, we can optimize the productivity of the system. The system now being our process our process plant or our refinery or our separators or whatever vessels or components that we are going to be dealing with. We can optimize it. We can optimize its capacity. We can know what is the optimum operation capacity. In fact, when we use HISIS in determining the optimum opera, the operation capacity of any of these devices or any of these equipment, not devices, equipment, any of these equipment like separators, um, um, mixers, refractors, compressors, expanders, and the rest of them. This or even pumps too. We use HISIS in designing their or obtaining their optimum capacity, operational abilities. That's operation conditions. All right. Now we also use it for equipment side call just came in. All right. So I hope you can hear me. All right. If you can hear me, I'll go on. Now this is it. Sorry. All right. This is it. This is how the whole simulation, it looks like some kind of funny thing, but this is what a simulation process looks like. All right. This is a process, an example of a process model. All right. Now, in this process model, over here, what we have, please follow the cursor. You can see how the cursor is moving. What we have here is a feed that is and also another stream. A feed, what we are calling this feed, not the front end engineering design I meant. This feed now means inlet or flow of of fluid. You understand, like a stream, all right, that is coming in. So we usually also refer to it as feed, as in like food. Okay, so it comes into a mixer, and we also have another inlet here. That stream is coming from somewhere, which we'll come back to. All right. So because this is a closed circuit, so this is the chemistry of what happens in a simulation. You can take snapshots of it while I'm talking. so you can still go back and revise it. Now you have the feed coming in. This is a mixer. Please mind you, this is not the feed I mentioned in our first class. This is not the front end engineering design. This is a stream. Okay, please, it's important you note that. Then it comes into a heat exchanger. It comes into a heat exchanger. What does this heat exchanger do? It helps to increase the temperature of the fluid. Now you can see some things that are being mentioned here. We are talking about steam rate, we are talking about recycle flow, we are talking about catalyst, we are talking about chemistry, we are talking about um, reactor type, you know, we are talking about the number of trays and feed, blah blah blah, and all that. Now this a typical example of a refinery or a fractionating process for a fluid. This is a typical example of a fractionating process for crude. Now, what happens here? Just follow me, please. Just follow me, please. All right. Here you are going to have what now? The feed comes in, and another stream is also coming in here. That is a recycle stream that comes in there. Now they get mixed up. It gets mixed in this mixer here, and then it goes to the heat exchanger. From the heat exchanger, it goes on to the you can see steam entering the heat exchanger. That's to increase the temperature. That's to help us increase the temperature of a heat exchanger. All right. Now, the heat exchanger increases the temperature of the fluid. All right. Now, so what is eventually entering this reactor? This reactor is like a mixer. Is a heated fluid. So it does some mixing there. Catalyst is also added. Then we now have to discover that in this reactor, the temperature and pressure will also be able to be detected using this simulator. All right. Now the software helps us to draw out by itself. It helps us to bring out all these features that we are having. The software brings them out as when you start operating it. All right. So what happens from here? This is what we call a process flow diagram, or this is a process flow diagram, PFD. All right. Now from here, from the reactor, we go again to another kind of heat exchanger, or a cooler this time, that now brings it, a heat exchanger, sorry, that brings it straight into a fractionating column. This is a fractionating column. These lines that you see are all trays in your fractionating column that is used in the refineries for the fractional distillation of crude oil. It is used for the fractional distillation of what? Crude oil. All right. So quickly, from there you can see that you have an upper stream, you have some collection on top here, and you also have some byproduct under. Now the stream on top here is sent again to for further separation into this kind of fractionating column. And you can see somewhere around here that steam is usually added to increase the temperature of this fractionating column, because by in refinery processes, if you remember your refinery very well, there are two factors that are responsible for the separation of crude oil into its different fractions. All right, those two factors are: number one, the but their difference in boiling point. The boiling point of methane or of kerosene is different from that um, of DPK. I'm sorry, of AGO, or gasoline, or that's our what we call our diesel. You know, it's different. The boiling point of methane is different from that of petrol, which is our gasoline, or our gasoline, or PMS, premium motor spirit. All right. So you can see that this factor is what is responsible for their separation inside this tray. But HYSYS helps us to calculate this, to determine it, and to model it. All right. This is a proper sequence with respect to modeling. This is a proper sequence. So here what happens is this. What is collected on top, which is gas, usually we collect the clear ones, and then there's a recycle process. There's a recycle process around here. There's a recycle process around here that takes that to now become a feed again. So those gases come back all the way, they are channeled back into this mixer for proper separation. Why? Because some of the gases that may be collected here may still have some content of um, crude or of oil or impurities in it. So it will be brought back into the system. That's why we call it what? A recycle flow rate. So that is a recycle for you. This is a typical example of what happens in HISIS simulation. What we have here is what we have here is now a purer component is what we now have around this point. All right. So the model in HISIS typically we have two states of modeling. We have the dynamic state and we have the steady state. Please take note of that. The steady state, we have a steady state and a dynamic state. In a steady state, you can see what you can from what you can see here. In a steady state design, what you usually have is that the input minus the output is equal to zero. What it means is that input will be equal to output. Whatever we are feeding in is always equal to whatever we are getting out. That is a dynamic state modeling. All right. So there we have our design, operation, and optimization as the major factors. So if you plot a graph, this is what it usually looks like for steady state. It will get to a point where you have a point of interception here of the different of your input and your output. All right. So you can see this equation here. What we mean by steady state. This is the feed. Now this is the vapor out output. This is the liquid output. So what steady state means is that the feed will be equal to the summation of the vapor output and the liquid output. Nothing is lost. All right. But in dynamic state, it is a little different. In dynamic state, we have our feed, then we also have some other introduction of pressure control, level controls, some other control measures put in place in this case. Now in this case, what happens in modeling, what happens usually in dynamic modeling is that you always have accumulation coming in. Accumulation means that there will still be some leftovers. There will still be some material to be balanced. So in dynamic modeling of HISIS, input, please take note of that. Input minus output is always equal to accumulation, and this is a graphical representation of what we have in dynamic modeling. So if you want to use the equation of state is that we have if we take the differential coefficient of the volume against time, that's dv dt. I believe many of us did differentiation in our O levels, but even if you didn't, what it just means is that the change in volume, over time, the change in volume over the change in time gives us the change in volume over the change in time gives us what now? Our feed minus what now? The vapor plus the liquid. So our dvdt is equal to our feed minus the vapor plus what? The liquid together. So that's a dynamic modeling in HISIS. All right. Now, the uniqueness of HISIS. This is very important for you to take note of. The uniqueness of HISIS. Number one is that it is very interactive. We have interactive simulation. HISIS, we ask you, we ask you, what do you have? when you put as in a colloquial way now, when you put in what you have, ISIS gives you what you want. That's how I usually put it. ISIS gives you what you want. It is very interactive. It will ask you of some things, some quantities that you need, that you have, that you should have. So when you have those values, whatever values you now put in, it will give you the result. It will calculate, do all the necessary and complex calculations and present it to you in an automatic way. All right. Now, another thing again is that HISIS is also, it also helps in the automatic detection of degree of freedom. It helps you to automatically detect degree of freedom. It also helps for steam flash calculation. When we're talking about calculations that involve change in pressure, temperature, and volume. We're talking about flash calculations. Okay, we're talking about bubble point, dew point, and the rest of them. These are stoichiometrical calculations in chemistry. All right. Now, HISIS helps us to do all that. Now, another thing it does again is that it has a very good interaction with Windows Microsoft program. Yes, it can present your results in an Excel format or in Word format. So by your clicking and your click, copy, paste, object, and the rest of them, those basic functions that you have in Microsoft Windows. Okay, HISIS is able to do that for you, copy and paste and all the rest of them. So it does that. It is also a bi-directional calculation. It also helps in bi-directional calculation. What we mean by bi-directional calculation is that it can calculate in two ways. It does not have to just calculate only one line. No, it does complex calculations. It can calculate in two directions, non-sequential calculations. It can be calculating for heat flow and also at the same time be calculating for flow rate of the fluid. Calculating the flow rate of the fluid and at the same time be calculating the heat changes that got to do with the fluid. You can be calculating pressure of and at the same time be calculating mole fraction. You know, that's what it means. Now it's easy to learn and use. Then it is also very fast. It's a very fast solver. It solves things very fast for you. The extensibility, man, is second to none. You know, then it is fully integrated. It has a fully integrated steady and dynamic state, which I was explaining before. Steady and you can simulate steady on steady state, and you can also simulate on dynamic simulations using HISIS. It's a very, very interesting tool. All right. Now, degree of freedom. I mentioned something about degree of freedom. What do we mean by degree of freedom? The degree of freedom is talking about the number of um, of independent parameters that define a configuration. Independent parameters, the number of independent parameters that will define any configuration is referred to as our degree of freedom. It's not rocket science. When we're talking about parameters as in unknown variables, you understand the number of variables minus the number of equations. You understand? That gives us the degree of what? Freedom. You can see something like a simultaneous equation now, for instance. All right. So once you have that, you are dealing with a degree of freedom. We'll be having some variables. You might know flow rate and you know mole fraction, but you don't have the temperature at which it may be operating. HISIS will help simulate that. You might know some, you understand what I'm saying now. So one or two variables that you might know, HISIS will use those variables to help get the other unknown variables. All right. So the degree of freedom in process balance. Please, before I go too far, it's very important. I show us the assignment. It's very, very important. I know many of us had some challenges. Some of the feedback I got from offline. Some people had a little challenge with your assignment, please. It's very important to take note of All right. Okay. While we're all right, let me just. I'll read them out. I'll read out the assignments in the next few minutes before we end. So, all right. In the next few minutes. All right. So this is what degree of freedom talking about here. We have uh degree of freedom being what now? In a process balance to mean the number of unknown variables plus number of reactions minus number of independent material balances and minus the number of relationships. I will explain that right now. Okay. Now, this is what it means. When you have an inflow here, imagine this scenario where we have